Hey guys, and welcome back to another weekly programming problem. Now in today's video, what we're going to be doing is implementing what's known as a tree data structure, and we're going to be doing this to simulate a dictionary in Python, except we're going to be programming all of the different methods and things that we need. So we're essentially going to be like writing our own dictionary in Python using what's known as a tree data structure. Now I'm going to talk exactly about what a tree data structure is, and the main problem solving aspect of this video is it involves a little bit of recursion and kind of thinking to figure out how we would actually go about implementing what I'm going to show you in code. Now I've kind of designed the main layout of the class in terms of the different methods that we're going to need and this node class, which I'll talk about after. But essentially, if you think about a dictionary in Python, this key value pairs. So you have, for example, the key maybe A correspond to a value of 8. You have the key Z corresponds to something. So we're going to be simulating that in a tree data structure today. So let's talk about what a tree data structure is quickly. So essentially a tree data structure, and in this case, we're going to be setting ours up as a binary tree, is something that kind of cascades down. So it starts with a root. So we'll call this R for root. And then there's branches that go off the root. So 2 branches for a binary tree. And there's some nodes. Okay, so all of these things are called nodes that I put little lines on. And each node can have at most 2 children and 1 parent. Okay, so this would be known as the parent to these 2 child nodes here. Okay, so on each child node, again, we can have up to 2 branches. So we can branch off again into a few other nodes here, and we can just keep going and keep going and keep going into infinity. Now, the way that a binary tree works in terms of computing, at least when we're using numbers, is something like this. So the way that I'm going to set up my binary tree is the root is going to be the first element that's added into our tree. So for example, if we have the element A, it goes there. Now the way that the child nodes work is that the child node to the left of any given node is always going to be smaller than that node itself. So for example, it's hard to do with letters. Maybe let's just use numbers actually. If I do if I put 3 here, only numbers that are less than 3 can go on the left side here of this node. So if I want to add 2, I can put it here. But if I want to add the number 4, it has to go to the right of this node. So the left and right side of each branch coming off of the node actually matter, and it's what's going to allow us to do some operations very quickly on our data, and you will see what I mean by that in a second. So for example, we have 3, we have 4. If we want to add now 5 into this tree data structure, well, we have to follow the same rule as before, where we can't actually put anything that is greater than 3 to the left of it. It has to go to the right side. So what we do is we say, okay, well, we can't go here in this empty node. So we go to the right and we check if a node exists there. This node exists. We're not going to move it, but what we're going to do is we're now going to branch off from this node and add our next number. And we want to add 5 in this case, so we have to follow the rule, and we say that, well, we can't add 4 on the left side because 5 is greater than 4, so we have to add 5 on the right side. So now we've added 3, 4, 5, and we have 2 blank nodes. These don't actually, I'm just putting them here so you can see that they won't actually be in our program yet until we add another number. But now let's say we add the number, I probably should use some different numbers so I could add something here. But let's say we add the number 2. If I add the number 2, what I would do now is 2 would go here because, well, obviously 2 is less than 3, so it goes on the left side, and then we can add it there. Now, let's say I want to add the number 2.5. Well, 2.5 is less than 3, so we go to the left. Now we're at this node, so we check 2.5. We say, is that less than 2? No, it's not. It's greater than there. So now we add another node, and we put 2.5 here. And this is the tree data structure that I want to simulate inside of my Python code. And the reason I want to do this is because if I'm looking for a certain node, say I'm looking for 4, I can find it much faster than if I just had everything set up in a straight line. So for example, if I had 2, 3, 4, 5 like this, okay, and I want to find 5, I have to look at 2, 3, and 4 before I can get there, right? But now, if I have my thing set up in a tree data structure, what I can do is I start at the root, which is 3. So I'm going to go to 3, and then I hit 4, and then I'm at 5. So I've now skipped one operation. Obviously, this is a bad example to show you how fast it runs because there's only 4 nodes, but when you're dealing with millions of nodes, if you know to move to the right or left based on the value, because everything's kind of sorted in here, right? Then you can find values very quickly, you can modify them quickly, and you can add things quickly rather than having to look through each single node in your list, which is just not efficient, okay? So this is what we need to simulate. So there's a few things we need to think about. We have to think about how we're going to add something into here. So we have to follow that procedure if we want to add a new node. We have to think about how we would find a node and get like the value associated with that node. We have to think about how we can figure out how many different nodes are in our tree and how we could possibly get all of them and look through the entire thing, right? So what if we want to print all of the different nodes that we have in here? That's another problem that we have to figure out how to do. So let's now go into implementing this and start writing some code. So I'll try to explain it as we go through, but I mean, it's not super complex. It just requires a little bit of thinking. So the first thing that we're going to do is contains. Now contains is essentially is a certain key inside of our tree. So remember, we're going to do this as a dictionary, which means we're going to store node objects, and each node object has a value of right, which is going to be the right child, left, which is going to be the left child, and then a key and a value. And the key will be what we store in the tree, and then the value will be mapped by each key, right? And just the way a dictionary works. So given a key, we need to figure out if it's inside of our tree data structure. So to do that, we have to look through our data structure and traverse it and find that key. Now, what makes this easier to do now is that we know that everything in our data structure is in that specific order. We know that everything to the right of a certain node has to be larger than it. So we can use that fact to find our key way faster than just looking through every single, key or node inside our tree. So to do this, I'm just going to set up a few variables. I'm going to say found equals false and current equals self.root. Now, whenever we set up a tree data structure, we have to start with what's known as a root. And that root is the only thing in our tree that doesn't have something above it. So like the root of the tree, essentially, right? What's holding it together is that root. So we start by defining a root that's equal to none because we don't have anything in our tree. So I'm just using a class, obviously, to do this. So what we're going to say is current is equal to self.root, and we're going to change this variable current and keep moving down a certain path on our tree until we find the value we're looking for or until we don't find the value we're looking for. So now what I'm going to say is I'm going to say, wow, current does not equal none, and found equals false. So essentially, until we reach a point where we don't have any left or right branch, or until we found the element we're looking for, keep looking through the tree, because we're going to look through the tree in here. And you guys will see how this works in a second. So what we're going to start by doing is we're going to say if current.key, because current is going to be equal to one of these node objects, and you guys will see how that works in a second. If current.key is equal to key, then what we're going to do is simply say found equals true. Because we don't actually care about the value associated with the key, we just care if it exists. So we'll simply, now we can even skip down to the bottom of our method here and just return found. So if we make it out of this loop and found is equal to true, then we will return that, right? All right, so our next thing now is if the current key that we're looking at, so right now in this case just the root, isn't equal to the key that we have, or that we're checking, we have to see where to look for this key next. So what we're going to do is we're going to check the current key that we're looking at, so in this case the root, and determine whether we want to move left or whether we want to move right. And I know I just did that reverse for you guys, but for me, I guess left and then right, okay? So what we do now is we're going to check if the current.key, well actually we'll check if our key is less than current.key, okay? And this will work, the less than operator, just assuming that the keys are going to be the same type. We're going to assume that each key that we put in here is going to be the same type, so like a string, an int, something like that. So if that's the case, then we will move left. And what we'll do to do that is we'll say current is equal to current.left. Because remember, each node is going to be a node object, and they all have a left and right value. And these left and right values are going to be other node objects that are their childs, right? So we'll move to the left. And then we'll say otherwise, so I guess we can just do else. We will say current equals current dot right. So now what we'll do is we'll traverse through the structure and try to determine whether or not some certain key exists. And we can do this very efficiently because we know whether or not to move right or left based on the fact and the way that our tree works, right? So let's do a quick example of traversing this. So for example, if we're looking for the number 5, right? I'm just drawing with my mouse right now, so give me a break. But what we're going to do is we're going to check this root node first, and we're going to say, okay, so is 5 greater than or less than 3? It's greater than. So let's go to the right. So now the current node we're looking at is this one, so node 4. Okay, now what we're going to do is we're going to say, okay, well, is node 4, does it have a value? Yes, it does. So let's keep looking. We'll say, so is 5 greater than or is it less than 4? It's greater than, so let's go to the right. Now we check 5. We say, oh, this is equal to the node we're looking for. There we go. We're done. We found it. Okay, pretty basic example. Let's say now we're looking for the node 7. Okay, what we'll do is we'll go to 3. We'll say, are we greater than or less than 3? We're greater than. Okay, so we go to 4. Are we greater than or less than? We're greater. We go to 5, and then we say, are we greater than? Yes, we are. So we try to go to this node here, right? But no node exists. So that means that 7 does not exist in our tree, because if it did exist, it would be further down on the right branch. And obviously there's nothing on the right branch past 5. So we know that 7 doesn't exist. And that's how we traverse and see if something exists inside of our tree data structure. And it's going to be the same similar idea in terms of adding things and getting values of certain items as well. Okay, so the next thing we need to do is update. So update is going to add a node into our tree data structure. So to do this, we need to first check, or there's a few different cases. So the first case is that our tree data structure is empty, in which case we need to define the node we're adding as the root node. Other cases are the node already exists or the node doesn't exist. So in those cases, it's a similar solution, but let's do the first case, which is that no nodes exist and the root node is empty. So in that case, we'll say if self.root equals none, then what we're going to do is we're just going to say self.root equals, and in this case, node key value, because our node object takes a key and a value, and that's it for that case. Otherwise, what we're going to do, similar to this, is traverse our list until we get to a point where we need to add our node in there. So what we'll do is we'll literally copy this with current and everything, and we'll just get rid of this and found thing because we don't need that. And now what we're going to say is, well, this actually handles all of our different cases, because if you think about it, well, if the current.key is equal to the key, that means we've just found where that our node exists, right? And we need to now update that value, because if you have a dictionary and you redefine a key with a new value, it's just going to override that key. So in this case, if current.key is equal to key, instead of saying found equals true, what we'll say is we'll say current.value equals value, and then we'll just break like that. Now these next cases, moving left and moving right, again already handled for us because we'll just keep moving left and moving right. But what we should check in here is if there is a left node or if there is a right node. Because if we try to move to the left and there's nothing there, that actually means that that is where our object needs to go, right? So if we go back to our example and we're trying to add, for example, 7 into here, well, what we'll do is we're going to look for 7, right? We're going to keep going and find a place where 7 should go. So we go 3, we go to 4, we go to 5, and then we're going to keep trying to go past 5 to see if there's anywhere better to put 7. And in the case where there's nothing there, that means that that's actually where we should insert our element. So we need to check that. So to do that, what we're going to do is simply say if current.left equals none, then what we'll put in here is we'll just say current.left equals node, and we'll say key value like that, and just break. And we'll take the same thing here and we'll put it here, and instead of current.left, we're going to say current.right. And that is it for adding elements into our tree data structure. That's how we do it using this simple method. Now to get an element, we're literally going to copy this exact same thing from contains. We're going to put it here and we're just going to remove found. And in this case, what we'll do is instead of saying found equals, so let me move found from here as well. Instead of saying found equals true, we're simply just going to return current.value, because when we say let's get this key, we want the value associated with that key. So in this case, we'll just return the value, and then say we get to the end and we haven't found that key. Well, we'll just return none because that key didn't exist in our data structure. Okay, sweet. So now it's time to get keys and values, and this is a little bit more difficult and where the recursion comes in. So essentially, we need to look through every single element in our tree data structure, because that's what we want to do here. We want to get every single key and every single value in our data structure. So how can we do that? Well, to do that, we need to take every single possible branch and essentially add all of those nodes or all those keys or values into an array and return them, or into a list and return them. So what we need to do is we need to go on every left branch and every right branch of every single node. So we got to we got to traverse through every single node. So how do we do that? Well, there's a few different ways to do it, but we're going to do it recursively, and we're going to use this function traverse to do so. So inside of my keys, what I'm going to say is I'm going to say ARR equals this, and I'm going to say traverse like this, but I think we need to do self.traverse, my bad. Self.traverse, and then here we're going to do self.root ARR. Now I'm just going to pass it the route that we want to start traversing at, and then an array, which is going to be here, where it's going to add all of the nodes it finds into that array, so that we can then return that array, which will have all of the keys, okay? So inside of traverse, how do we traverse every single left and right branch? Well, it's actually pretty straightforward. The first thing we need to check is if we've reached a dead end. So for example, if we start traversing through this right here, and we get to here, well, we've reached a dead end, so we don't want to go left and we don't want to go right anymore. And that's actually our base case for recursion, which we're about to do, is once we reach a node that doesn't exist, so we try to go left and we end up having none, well, that means that we can't go left or right anymore, so go back and do the next step. That's what we need to do. So if I go back to subline here, what we'll do to do this is we'll start by checking to make sure that the node we're passed is not equal to none. So if current does not equal none, okay? Now, if it doesn't equal none, what we'll do is we'll get whatever that node is and we'll add that value or the key into the array. So to do that, we'll say array dot append current dot key. First step, very straightforward. And then what we'll do is we'll try to go left and we'll try to go right. So we'll say self.traverse, and what we'll do is we'll say current.left, and we'll pass it the array, and then we'll copy this and we'll do the same thing, except we'll try to go to the right. So this is our recursive call, and this is actually all we need for this function. But essentially the way this is going to work is we start by calling it here on the root node. We give it an empty array, or list, sorry, and what happens is we're going to check to make sure the node we're given is not blank. So in this case, we'll start at the root. We'll say, does the root exist? Yes, it does. Okay. So what we'll do is we'll add that root's key into our array. And notice it's actually going to change this array because arrays are mutable objects. And this is a nice, clean kind of way to do this. And then what we'll do is we'll try to go left and we'll try to go right. So we'll say, okay, so that node wasn't blank, which means it should have a left and it should have a right. So let's try to go to the left and we'll pass that same array. So we try to go to the left. So what we'll do now is we'll say, okay, so now current is equal to the root's left node. And now we say, all right, so does this node, does it exist? Is there something here? If there is, we'll add that node into, the array. And then we'll try to go to the left of that node and to the right of that node. So if I show you on the diagram here, I got all this stuff everywhere. But essentially, let's change to red so we'll start here. We'll say, is this blank? So no, it's not. So what we're going to do is we're going to try to go here and we're going to try to go here. So we'll start now. We're on this left node. So what we do is we say, okay, so we'll add this into the array. And now we're going to try to go here and try to go here. Well, both of these are dead ends. So that means, all right, we're done now recursively checking this path. So now the next call on our stack is here. It's 4, right? Because that's what we were going to call after we traverse through all of the nodes on 2. So what we do is we go to 4. We say, okay, we're going to try to go left. We're going to try to go right. We start by going left. We notice that this is a dead end. So we stop going that direction. And now we go right. And now we say, oh, well, there's a node that exists here. So add that into the array. And now we're going to try to go left. We're going to try to go right. Okay, there's nothing left, but there is something right. Let's add this to the array. And then we try to go left, we try to go right, and it's empty on both of here. So now we're done all of our recursive calls because there's nothing more being called, and we've traversed through the entire tree data structure and added all of those elements into our array. So now we can return the array and get all of the keys. Very straightforward. Now values is really easy. We've pretty much already done it. So this is giving us all the different keys. But if we want the values, let's just say keys equals self.keys. I don't even know if I can actually call it keys. This might be an issue. Let's just say ks equals self.keys. And then what we'll do is we'll simply say return a list where we're gonna say what is it? Self.get, and we'll say k for k in ks, which means that we're going to get all of the different keys. And then for all of those keys, let's get the values associated with those keys and return that. So I've added a few little tests here just to add A, C, and then B, and then to change B to the value 4 to print out the keys, the values, and then try to get the value of B just to make sure that our data structure is working. So if I want to run this, I'm just going to go into my command prompt and just go Python problem 8.py. And we notice that we get the 3 keys that we had added there. So if I scroll down, which are A, C, B, I know they're not in order, but that's fine. We could sort them if we wanted to. And then we get 2, 4, 4, which are the associated values with those keys. So we have essentially set up our own dictionary in a tree data structure by using 2 classes, so a node and a tree. And we found a way to traverse through the entire data structure recursively. And the main advantages of this data structure are it's way easier to find certain things because we know automatically to go left or right. So it becomes almost instant to find certain elements in our data structure, obviously depending on how many there are. And it's way faster for some operations than just having, for example, a linked list or a standard list like this. So anyways, that has been it for this kind of tree data structure problem. I know this wasn't really a programming problem, but to be honest with you, I need to study for my computer science exam, which is in 2 days, and this is one of the main topics on it. So that's kind of why I'm making this video right now, to kill 2 birds with 1 stone. But anyways, I hope you guys enjoyed. If you have any questions, make sure to let me know in the comments down below, and I will see you in another video.